Okay, so let's look at a few equations. If you are not comfortable with equations and you are from biology or social science or whatever, just try to understand the concept and manage somehow. Okay, it's not a very difficult calculation, but it is very important. But you should get the general idea of what actually happens. Okay, so what are we talking about? Essentially, we are looking at global energy balance first. So sun is emitting energy in all directions, and we have changed this number a couple of times already, but doesn't matter. We said we can look at the energy and fit curve to it, Planck's curve, and look at the maximum temperature at which energy is being transmitted, and it's around 6,000 Kelvin. And Earth is receiving energy from the sun mostly in the visible, and it's emitting energy out at 255 Kelvin on average. So we have to understand the balance, and the energy that is starting from the sun and reaching the earth has a formulation like this. So if we look at energy at the top of the atmosphere before it has gone through the atmosphere, greenhouse, etc., etc., it is going to be determined by the energy flux that is leaving the sun divided by 4 pi r squared. What is 4 pi r squared? Let's say we put a sphere around the sun, because imagine sun is 3D and it's going and it's sending out energy in all directions from the sphere, and there is a sphere around it at some radius at which you want to know how much energy is coming in. So let's say we take Earth and we put a sphere above the atmosphere, and that is at a distance of r from the sun. How much energy per unit area of this sphere around the Earth is arriving from the sun? So that is the solar flux, Q divided by 4 pi r squared, which is the distance from, let's say, the center of the sun to that sphere. Okay, so the Earth radiates energy at the same rate it is received from the sun. The Earth's emission temperature is 255 Kelvin, and that of the sun is 6,000 Kelvin. The outgoing terrestrial radiation peaks in the infrared spectrum. The incoming solar radiation peaks at shorter wavelengths in the visible spectrum, as we already saw. So it has a full electromagnetic spectrum, but maximum energy, as we saw, is at the visible range. Okay, so what are the things we need? Just to add some extra information, properties of some of the planets. S0 is the solar constant at a distance r from the sun. Alpha P is the planetary albedo. It is basically the reflectivity of any planet, how much of the sun's energy is just being reflected. So if you imagine urban center versus a desert versus a snow versus ice versus forest, the reflectivity to sunlight is very different. For the ocean, the reflectivity even depends on the angle of the sun, for example. So that is something that's critical to determine how much of the energy actually stays and how much is just thrown back immediately. TE is the emission temperature computed from equation 2, which we will see. Tm is measured emission temperature. Ts is the global mean surface temperature, the rotation period in Earth days. Is this really important? Not really. What I want you to notice is that Venus received more energy per unit area than Earth because its distance is shorter. Mars receives much less energy than Earth, and their reflectivities or albedos are also different. Earth and Mars are fairly close to each other, but Venus has a very high albedo of 0.77, which means 77% of the energy is, from the sun is being sent back without even doing anything. But the emissivity temperatures of Venus is 227. For Earth is 255, as we mentioned. For Mars it's 211. So Mars is quite cold. The mean emission temperature is 230, 250 and 220, but what are we most interested in? Typically, it's the surface temperature in Kelvin. So if you look at the surface temperature of Venus, it's 760 Kelvin. For Earth, it is 288 Kelvin at the surface. So this 255 is at the top of the atmosphere. Make sure you understand the difference. Okay? Energy coming in is doing many things in the atmosphere, coming to the surface. Surface is doing many things. So there is a energy that is going out from the top of the atmosphere, and there is temperature at the surface. So surface temperature is 288 Kelvin. Why is this different? Because of the greenhouse effect. So look at the greenhouse effect here. Its emission temperature is 227. Its measured emission temperature is 230. And its surface temperature is estimated at 760 Kelvin. So it has a runaway warming, as we mentioned before. Mars, on the other hand, is quite cold compared to Earth, minus 50 degrees centigrade. So its surface temperature is at 230 Kelvin, and there are differences in the rotation period as well. Okay, so albedos for the Earth, ocean depends on the angle of the sun. Forest 6 to 18%, cities 14 to 18%. So just look, relatively speaking, desert is much more reflective, soil is not, forest is not. Clouds can be very reflective or not, depending on their depth, how tall they are, what is the temperature at the top of the cloud, and so on and so forth. Snow has a relatively high reflectivity, and fresh, that's old snow. Fresh snow has very high reflectivity because it's very white. It can reflect a lot of the visible radiation from the sun. So the calculation will go like this. Let's say we have Earth rotating around its axis. Let's not worry about the angle, the tilt to the orbital plane yet. So the sun's energy is coming in, since it's coming from pretty far away, is fairly uniform. So Earth is rotating around its axis, but we are interested in how much energy is being intercepted by the Earth. How do we figure that out? We look at the area of the sphere that is projected to the sun's energy coming in. So if you take a basketball and shine a light on it, its reflection will be a circle. So here is the circle. The area of the circle is pi a squared, where a is the radius of the Earth. Okay, so the spinning Earth is imagined to intercept solar energy over a disk of radius a and radiate terrestrial energy away isotropically from a surface, which means at each square meter energy is going out. Okay, so the intercepted energy is related to the area that is always projected to the sun, and outgoing energy is going from every point on the surface. Just listen to it and make sure you understand. It's very kind of subtle, but still very important. So here is the distribution of surface albedo. Where there is ice and snow, you have very high albedo, almost 0.8, 0.9. Deserts have high reflectivity, snow, forests, lower, urban areas, and so on. Earth's average reflectivity is about 0.3, which means Earth on average sends 30% of the solar energy back to space. What do we do now? So we take the energy that is being intercepted by this circular disk that is facing the sun all the time. Even though Earth is rotating, there is always a circle that is receiving energy, right? So S0 is the energy per unit area arriving at the at the top of the atmosphere. Take that, multiply by the area of the disk that's intercepting the energy. That gives you this number of 1.74 times 10 to the 17 watt. So the energy coming in is about 342 watts per meter squared, but when you multiply it by an area, the meters per meter squared is gone, and you have total energy. Solar radiation absorbed by the Earth is going to be reduced by the effective albedo, which is 30%, as I said. So only 1 minus the albedo is what is kept in the system, because 30% is reflected. So about 70% of this number is this 1.22 times 10 to the 17 watt. Okay, so just remember, this is about 0.3. This is the average. This is, if you average this all over, you will get about typically 35 to 40 30% is the total albedo. Okay, net albedo. So emitted radiation per unit area. Remember that Earth is emitting radiation from every point on the surface of the sphere, and this energy is the black body radiation that we mentioned before, which is sigma TE to the fourth, where TE is the emission temperature. Okay, we are not saying where it's coming from. Earth is emitting temperature from somewhere, obviously not from the surface because there's an atmosphere, obviously not from the top of the atmosphere because energy is going out from many levels in the atmosphere, sometimes directly from the surface through the atmosphere to space, so it's a bit complicated. But there is some effective emission temperature TE, and the energy going out per unit area is sigma TE to the fourth. How do we get the total energy going out? We obviously take the energy per unit area and multiply by the surface area. So that is going to be energy received, net energy received, and emitted area per unit area to total terrestrial radiation, which is per unit area multiplied by area of the sphere, which is 4 pi a squared. So 4 pi a squared sigma TE to the fourth. So we basically have to take the energy, net energy being received, and equate it to the net energy going out, and that gives us the expression for the effective emission temperature. This is a very simple thing. We haven't done anything yet. Okay, so you equate this to this, and you solve for TE. What do you get? You get effective emission temperature is related to solar flux per unit area, albedo divided by the Stefan-Boltzmann constant to the 1/4. We know all these numbers. This is about 342 watts per meter squared. This is about 30%, 0.3. Sigma is some number that is got a certain unit. When you plug it in, you get emission temperature of 255 Kelvin, which is the which is the temperature we said that is observed at the top of the atmosphere. But we are interested in what's happening at the surface, because the surface temperature is not just about a short wave coming in and long wave going out, but there is a lot of things happening in the atmosphere in terms of greenhouse gases. What is surface temperature? That's what we want to know. Okay, so Wien's displacement law, I won't bother much with it. We already saw that when you do the Planck's curve, the temperature and maximum wavelength are related to each other. So it says that maximum wavelength of the energy being emitted by a black body versus at times temperature is constant. So if you know the average temperature, let's say of the sun and of the earth, then you can take this constant and find the average wavelength of earth's radiation. Okay, do we really need to know this? If you want, you can stare at this for a little bit and you will understand. Okay, so this is the temperature. Obviously it's too cold if you consider the surface temperature or average temperature of the atmosphere. So where is that temperature coming from? Obviously we have to start adding complexities in terms of greenhouse gases. So we have to add an atmosphere, which is what we will do in the next podcast, because this one is already almost 15 minutes long. Okay, so just remember, Earth is a sphere rotating around its axis. It is always projecting a circle to the incoming solar radiation, which determines how much energy is being intercepted, and some of it is reflected because of albedo. and it is emitting long wave from every point on the sphere. So we equate the energy being intercepted at short wave minus the energy reflected at short wave and equate it to energy going out at each point on the sphere in the long wave. That gives us emission temperature of 255 Kelvin, but we know that the surface is not that cold, so we have to add the greenhouse effect to find the surface temperature.